Okay, hello everyone. Uh, Let me just start our lecture by just a little bit review of what we have from last Monday. So we are able uh, to summarize the higher order, okay, at least until several parts. This is when we are having the boundary value problem on the higher order, that we might have many solutions. We have just exactly one solution or no solution at all. And it's depend on what boundary condition we have, right? Okay. And then we are having the idea on homogeneous equations and non-homogeneous equation. And this is important because if we are going to solve the non-homogeneous equations, we are going to include the homogeneous one. Okay, so basically we also have the differential operators. This differential operators is just tools. Okay, when we are applying them, then we are going to operate the derivatives. Okay, and it's actually not really that uh, new knowledge. This is just a standard derivative. Okay? Differentiate one time, two times, three times. Okay? It depends on the equation itself. Okay? And the other important thing is the superposition principle. So when you have some sort of solutions, then the other solution, for example, you have y1, y2 as your solutions, then your other equation, which include y1 and y2 inside, it's also can be a solution. Okay, that's the superposition principle. Okay, and the other thing is the linear dependency. Okay, so we are going to find our goal is we are going to find the solutions y1 and y2 that is linear independent. Okay, so we are going to find the independent one. Okay, and to check whether it's linear independent, we call the determinant of Wronskian or Wronskian in short. Okay, so we are just going to plug in the row and column by the solution and its derivative. Okay, so if it is just one derivative in this differential, so we are going to just have 2 by 2, probably 2 by 2. If we have 3, we have 3 by 3. If we have 4, we have 4 by 4 matrix, and we are going to evaluate the determinant. Okay, and if it's not 0, then that will be our linear independent, okay, solution. And then aside from what we have, we are going to define our fundamental set of solutions. Okay, so if we are going to have any y1, y2, any numbers, okay, how many solutions we have that is linear independent solutions of homogeneous one, then it will be our fundamental set of solutions on the interval. Okay. And this will be the general solutions. Okay, when we have the fundamental set of solutions, we can make it in a structure. We can tailor it in y equals c1 y1 plus c2 y2 plus it according to how many solutions you have, and that will be your general solutions. Okay, for homogeneous equation, right? And then for non-homogeneous, remember that we have this homogeneous one, and this will be also included in the non-homogeneous one. Okay, and we are going to have, we call YP, the particular solutions for the non-homogeneous. Okay, so for homogeneous one, we have this part, okay, that we have already defined before, and for the non-homogeneous, we have YP. Okay, so the conclusions, the solutions that might have for non-homogeneous is the homogeneous one plus the particular solution of that non-homogeneous. Okay, that will be the general solutions. So we can have this y equal yc plus yp. Yc is our it came from the homogeneous equations, and yp came from non-homogeneous one. And for general solutions of non-homogeneous, we can say y is equal complementary plus any particular solution. Okay. Okay. And we also have the superposition principle for non-homogeneous equations. So suppose that yp is the particular solution, and they have several solutions for the particular solutions. Then we can tailor it into uh, our yp in the terms of several yp1, yp2, etc. Okay. Okay, that's the just that part is just kind of introductions on our higher order, and the method. One method is we call the reduction of order. So if you have y1, y2 that is linearly independent, and we already known y1, then we can find y2, which means that if this both solutions are linearly independent, then the ratio between y2 and y1 is non-constant or non-scalar, right? So perhaps there will be some sort of function behind this ratio. Then that is the idea that we are going to find. Okay. So for example, if we want to find y2 from these equations that has y1 e with power of x, then we are going to substitute the y becomes ux ex, and we are going to derive twice, and we are going to sub into the original questions, which is the differential equations, and we can finally define and get the answer. And the rest of the method is using the linear order differential equation. So we are going to force these differential equations that has this particular second derivative and first derivative. We are going to reduction. We are going to reduce the order. So this is right here. This means that this is the reduction of order. Okay. So what the meaning of this reduction is, we are going to force any higher order to become linear order, to force them to be linear order. Okay, so you can say that basically there are just limited equation that can be done through this method. Okay, first you need to know the y1, okay, or the one that you are supposedly works, the solution that's supposedly to be works, and you are going to substitute with ux, and then you need to find those u. Okay, and then in the middle, in the process, you can substitute with another variable, which is the w. Okay. The purpose is to reduce the order. So if you have the second order, you need to reduce to linear. And when you have the linear order, go with the integrating factor. So this is the same method with the first order linear, okay, that you already learned, which is the integrating factor, right? I think this is the method becomes more and more important, the integrating factor, because it will be you are going to use it more and more in the higher order. Okay, and then multiply as usual, and then finally finding what is u. Okay, what is u, and then later transform back to the original one. What is your substitution? Okay, then that will be your your solutions, your second solution. This is y2, okay, right? Okay, and then we get the general solutions for this differential equations. And this is just the general case and how we are going to solve. Okay, basically the same thing, okay, but it's more general using some symbols. Okay, I already right here. We take this substitution to reduce the order. Okay, so basically reduce and becoming the linear order. Okay, and finally we get the idea that this is what we have. So uh, either way, if you want to just write one by one, like the previous example, and using integrating factor, differentiate, integrate, and finding u, it's also okay. Or just using directly this equation, is also fine. You are certainly going to find the final answers. Okay, like this one, we are going to just input the formula, and then we get the second solution, and we can input the second solution in our general solutions, and that's what we have. Okay. Before we continue, is there any questions first? Any questions? No. Okay, before we continue, I would like just to check, okay, to check our comprehension before this higher order. Some of the first order, just want to check whether you are able to find. Uh, okay, let me stop the sharing first. Okay, let me stop the sharing first. Okay, let me share my second screen. Okay, we are going to have feedback first. Okay, it's a little bit different from our previous class. But I will have the feedback uh, in the early class. Okay. Okay. I just want to check. This is just I think it's three or two questions. Very simple. I think it's a little bit uh, calculations and checking. Okay. 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 I think I will start here. Yeah, just two questions. Just two questions. Okay. Okay, I think it's okay. Get ready. The first question. If I just give you this question, can you solve this? You need to plus A, B, and C. Uh, okay. You need to use substitutions for this one. I think not enough time, right? Or is it okay? Okay, yeah, no, correct. I think that's okay. I think the time is too short. Okay, okay, one more. I hope the next one is, I think should be easier. Okay, okay, Bernoulli equations. Okay, if you remember Bernoulli, which one is not Bernoulli? Which one is not Bernoulli? You will notice that the Bernoulli has a pattern, right? Okay, from this four, they has all patterns except one equation. Okay, except the C. Okay, okay. Please, Puffy, your name if you want to. Okay, Puffy, please write your name. I think you can write your name in chat box. Okay. Oh, okay. Okay. Don't forget your student ID or if you have any feedback. I think just too short, right? The first one too short. I believe this the first one. I think I give you 2 minutes. I think I should give you five, right? 5 or 6 minutes, right? I think it's okay for the first one. Okay. Okay, wait. Okay, now I will go to just a little bit explanations on the previous chapters, especially the substitutions. I think I need to give you a few examples. I think one or two that can be described as this. Uh, okay, let me check the questions. Okay, let me check. What is the questions? Okay, I think the questions from our feedback session before is x squared plus y squared, right? And then the wait, let me check. Yeah, the x over dy. This is the x over dy. The x over dy equal xy. And then we have initial value that is when x negative 1, y is equal to 1. Yeah, this is the same question, right? Okay. Now, what we are going to do here? Well, we might have, okay, uh, maybe the first thing is just rewrite this and maybe take it all to the left side and multiply all with dy, and then we have a 0 at the right side. Okay, now there will be some trial and error for some substitutions. You will see that when we have the process inside. The first thing, notice that we might have yx here. So probably just say that we have u equal ux. Okay, that's our first trial. Just try to sub it, and I think this will be work. This will be work. So first, or let me write the differentials first. The differential for dy is, we have the product rule. So x du plus u dx, okay, for dy. So x squared, still x squared, y becomes u squared x squared, okay, and dx still dx, minus xy, this become u squared ux squared, sorry, ux squared, okay, and dy becomes this, okay, x du plus u dx. We solve one by one. This become 1 plus u squared dx minus ux cubed du. Let me check, 1 plus u squared u squared, let me check, okay, and we can separate this. Divide by x cubed dx per x, divide by also 1 plus u squared. Okay. So we can cancel that, and the other one will be canceling, and u over 1 plus u squared du. And we integrate separately. So we are going to have separable method, and this will be ln x. Integrate using some substitutions. Let's say w, and we are going to have half, right? We have half ln 1 plus u squared equal a constant. Now we have ln x over square root, right? Or no, let me just write x. Oh, we can have this, yeah, a constant and we have this, and this is supposed to be becomes e with power of c. But remember, in differential equation, one thing that you need to compute is you can simplify any constant you have. So for example, if you change this constant becomes e with power of constant, that's still a constant. So you can just write this as a, let's say, constant 1 or constant 2, constant 3, or any constant symbols you want to write. Okay? So let me just write this becomes a constant 1. Okay, and this we can square all this, right? We can square and make it becomes, let's say, c2. That's still okay. It's another constant. That's the one thing that you need to keep in mind for every differential equation. You can make up any constant, and if it's still a constant, it's just a constant, and you can just write in the very final answer just a c. Okay, that's it. So if you are having a question that asking the particular c at the final solutions, which means that it's going to have the final constant at the very end. Okay. Now from here we are going to have uh, okay. Now u is what? Y over x, right? Y is ux, so u is y over x. So let me substitute back here and multiply with x squared, so it's become x4. This will be multiplied with x squared plus y squared, right? And then we have this initial value. So when x is -1, so c is 1 over 2, right? So solution is 2x, or we can say x4 plus c2, or maybe we can make it equal half x squared plus half y squared. Well, it can be, but then I should have this as an alternative answer also, that half plus 1. Okay, it's 2, or the one that I make up the solutions, that is 1 plus 1 plus 2. Okay, I should have give you this 2, but let me check anyone getting 2. I think, yeah, you didn't get also 2. So 2 or 4. Okay. I should mention that there will be no fractions in the solutions. Okay. Yeah, I forgot to mention, but that's how it works. So substitutions means that you are going to substitute y or x into u with something u or v for gx. The idea is to separate the equations and then solve the differential equation. Okay. Okay. Uh, and for some sort of particular equations, for example, let me give you just just a quick recap. Okay. For example, you have differential equations, that is, for example here, tangent squared x plus 1. Okay. If you're given specifically like this, then what you're going to do is probably you can just substitute with this using this expression. So you can say u is x plus y, and then substitute and try to work out some substitutions, product rule, and then finally having the separable method probably, and then that is your solutions. Okay? And what we are going to do here is we are going to have usually we are going to differentiate with respect to x. So we will have a du 1 plus dy. And then from this connections, we can also try to solve and substitute this t. Okay. And you will have tangent squared u, right? And then the tangent squared u, you can use some trigonometric identity also to simplify it. Okay. And another thing, like for example, another differential equations, 2 plus, let's say, y minus 2x plus 3. Okay. If you get this, then remember that the idea for substitution is to simplify your calculations, and also to see that if we can substitute, can we get the separable, can we separate the variables or not? That's the key for substitution. So here we can take this as our u, and then we can just play some numbers and try to separate.
Professor, I have a question. How about the dy dx of the both case? Like, how can we change the dy dx?
This one? You mean this one? Time?
Yeah, of both case. Yeah, of both of the case that you show us, the tan to the power.
Okay, okay. Let me just a quick solution here. So if we take this, okay, for the tangent, then perhaps this is our du, right? Du is equal y plus dy, and then we can have because our dy dx is tangent squared u, right? And we can exchange this. So first is, or maybe if I write the du with x of this, maybe it's going to help. Okay, okay. So we can write that du dx is 1 plus the tangent squared u, right? This is from here. Okay. Okay, and then 1 plus tangent squared is a secant, right? A secant squared. So we can have that as our identity as well. Secant squared. And then what next is maybe we can write du is secant squared u dx. But secant, probably you will be able to solve with cosine, because it's easier to think. If you have cosine, you can integrate easily, right? So maybe we can take this as cosine squared u du, right, equal dx, and then just integrate, right? I think you can integrate this, right? Remember, if you have sine or cosine having square, the idea is to get the double angle one from here, because let me write with alpha from here, or this can be, or this is just cosine square, so this one, right, the cosine square here. Okay, I think you can integrate this, right? And then at the end, change back u to x plus y. Change back u to x plus y. And I think the other one here is also similar case. And I believe this also, I think not too complicated here. So du dx is dy over dx minus 2. And du dx is this, right? And this whole thing is u. Then du dx is just 2 plus u minus 2. 2 plus square root of u minus 2, or just simply write du dx is square root of u. And then just doing the separable and then integrate both sides. Okay, so that's the key. So at the end, you will get some two variables at least and separate those two variables. Okay, I hope you get the idea. Okay.
Thank you, Prof. I got it.
Okay. Okay. Any other questions? So basically, substitutions. You are going to substitute either x or either x or y. Okay. One of them. Take another variable, and then make that variable becomes the new one that you are going to integrate at the end. Okay. Okay. Okay, I hope for the higher order, for the reduction of order, I hope it's clear and you can resolve that as well. Let me just go to some example. Okay, let me give you just a uh, quick short question on the reduction of order. Okay. Okay. Suppose that we have differential equations y double prime minus 25y equals 0. And suppose we have known solution y1 equal e with power of 5x. Uh, Find second solution y2x. Okay. Okay. First thing, in the reduction of order, we need to define this y2 as we call with some u, okay, u of x, multiply with e 5x. Okay, this is from y1, or let me write in more clear way. It's ux y1x. Okay. Now, if we have this y2, then we are going to define this y prime becomes, differentiate one time with a product rule, of course. Then we have 5 e5x ux and plus e5x u prime, right? And y double prime will be e5x u double prime plus this will be 5, right? So this I will write okay. and this will be okay. So we will have plus 10 e5x u prime plus 25 e5x u. Right? Now we have the dE, the differential equations is y double prime minus 25y equals 0, and we need to check whether this is correct. Okay. Now y double prime is e 5x u double prime plus 10 e5x plus 25 e5x u minus 25. Y is ux y1. Y1 is e5x, right? And this will be canceling this. This equals 0. Now we have e5x u double prime plus u prime, sorry, 10 e5x u prime. We have u double prime and u prime. Okay. Remember, in the reduction of order, we are going to have the linear one, right? So we are going to reduce the order. So reduce by substituting the w as u prime. So we will have so e so we have let's say we are going to have the w prime plus 10w equals 0. So we can see that we may have this integrating factor. So when we take this as e 10x w, this can be done from here, and we may have the w is u prime is equal to ce negative 10x, and u is, we can integrate, become, let me just write as a new constant, e negative 10x. Okay, because just e is just e, right? Just change the plus and minus. So second solutions is e negative 10x. This is the u, and then e5x y1 is equal to e minus 5x. Yeah, this is equal to 0, so we can cancel this. Or that will be because e5x will be not equal to 0, right? Okay. Or maybe let me write. If you confuse this part, I'm gonna write here. Okay. So u double prime plus 10 u prime is equal to 0. Okay. Okay, that is how we get the second solution. Just a quick recap, and I think we can continue a little bit. Okay, from this particular equations, we see that every time we have the e with power of something, that part will not always be zero, right? So probably we can say some sort of general condition, right? When we have homogeneous, linear, higher order, then probably we will have something on the relations between that. Okay. So suppose we have, let me just continue first. Okay. Okay, so let me write a n y n plus a n minus 1 y n minus 1. The the n is the n derivative. Okay. So the coefficient a I, where I is from 0, 1 until n, they are all real constants, and a n is not equal to 0. So the facts is most or all solutions of higher order differential equations either exponent or construct out of exponent. So you will see many e with power of something, right? Like the previous case that I show you. Then we begin to see from, let's say we have the second order differential equations. Okay. Let's say we have a y double prime plus b y prime plus c y. Let's say equals 0. Okay, let's say the solution is in the form y equal e to the power of mx. Let's say this is our solution. We check the first derivative. We check the second derivative. Right? We have all this equation. Let's put this into our equations here. We are going to have a m squared e mx plus b m e mx plus c e mx, right? And of course, we are going to see that we can factor out the e, because remember that the function e, its derivative is in or it has, or it brings out the same original functions, right? If we have e to the x differentiate, it's just e to the x. If you have e to 2x, you have 2e 2x, right? You still got the original equation inside when you derive many times for e. So that becomes one particular behavior that we are going to look on this differential equation. Then we can factor out e with power of mx. M. No, m just a symbol. This is just for general case. Okay. The m is just a symbol, just general case. Okay. Okay. So let's say the form has the solution e with power of mx. Let's say that's the solution for this general case. Okay. So we can factor out this, and we are going to have am squared plus bm plus c, right? Okay, so e will never be 0, okay? E will never be 0. Let me write e will never be 0. So the only one that has certain characteristic is this equations. We call these equations in your textbook, it's called auxiliary equation. Okay. And we can observe these equations as quadratic formula. Okay. So we will have three cases. Okay. We will have three cases from this equation. Okay. The first one, if the we call the discriminant. Okay, if you remember the quadratic formula. Okay, if you remember that the quadratic formula, we have m1 and or 2 is equal to negative v plus minus, right? Okay, and then from this formula we can have three cases, depends on the discriminant. So if it is positive, which means that we will have the real m1 and m2 will be real, and let's say distinct, which means we can distinguish from one another. If we have b squared is equal 0, then m1 and m2 it's real and equal. And if we have less than 0, then we will have a complex, right? This will be conjugate complex. Okay. Conjugate means we have maybe 4 plus 2i, like that. This is going to be called conjugate. Okay, now this is what we have. Okay, I haven't yet make the title. This is we call the constant coefficient. This is for homogeneous linear equations. Okay, but it can be also for higher order, but it should be linear. Okay, let's discuss a little bit on these three cases. Okay, what we have. The case one is the case that is very common, and I think you already have idea in mind. We will find for case one that the two solutions will be, if this is e m1x and y2 will be e m2x. I just write m1 and m2. These equations or these functions, okay, these functions, we can say that because of this is case one, this will be linearly independent on all x. Let me just write on all interval. And the general solution on this interval is, you can write it constant like that. Okay. This is for case 1. Okay, for case 2, we see that M1 and M2, they're both real and some sort of equal. Okay, now for the equal one, let me just write that M1 is equal M2, which means that the potential solutions is Y1 equal E. Let's say we have this M1x. Okay. So the only way we have M1 is equal M2, or let me just copy and make a new page to make it easy. Maybe cut, make it here. Okay, to make it M1 equal M2, need to have b squared minus 4ac equals 0 to make it equal. And then if you remember, from the reduction of order, we have this is y1, and then we have integral and then integrating factor here, right? So let me just write the second solution for this one. If we have, then we will have e m1x integrate e to m1x divided by e to m1x dx. So this will be equal to e m1x integration dx. This will be x e m1x. And remember, in the general solutions, we will have and also for the quadratic formula, remember that we have one way to have the m1 is from minus b over 2a. Remember the if we have the quadratic formula, and we will have the general solutions with the second solutions going from the reduction of order. Now the complex one is having a little bit complexity. Okay, so let me try to explain to you. So the case 3, is having a conjugate complex. Okay, so M1, M2 are complex. So we can write M1 is alpha plus I beta. I is the imaginary number. M2 is alpha minus I beta. Alpha and beta is both are positive. Positive and real number. Okay. And I the imaginary number, or I squared, is negative 1. Okay. So in general, we can say that the general solutions is C1e with power of a plus I beta x plus C2e a minus I beta x. Okay. We can say that this is general solutions, rough general solution. I mean, just say rough, because we can simply solve this in all real numbers, but we have a complex here. Okay. But we are not really, it's not a really practical way to work with, because we have a complex conjugate here, right? It's called complex. So we can try to manipulate this form and write in more practical way. And the way we are going to do this is we are going to use the Euler formula or Euler formula. Let me just telling you how to make it into this formula without saying like a complex definition of this formula. But let me just say, if we have the Euler formula, that is, if we have E with power of I theta, this will equal cosine theta plus I sine theta. Okay, where the theta is any real number now. It follows that if we have E with I beta x, okay, let's say beta x, this will be cosine beta x plus I sine beta x. Okay, and in the other hand, we will have negative I beta x equal, now it's negative. Okay, now we know that cosine in the negative, or in the fourth quadrant, is a positive. Okay, and sine in the fourth quadrant is becoming negative, right? Now we can add the e I beta x. Okay, we add plus e negative I beta x. When we add this, they will subtract. Okay, they will subtract, and we get 2 cosine beta x. And when we subtract this e, we will get 2I sine beta x. Okay, since we have this as our solutions, let me copy this. And what we are going to do is we are going to rewrite the solutions. Okay, provide the solution. Since we have this as our solution, then C1 and C2 need to be equal. We can make it equal 1, okay, to make so that we can exchange with the Euler one, okay, with the Euler, or we could make the C1 equal 1, C2 equal -1. So we will have at least some sort of solutions from here. That is y1 is e alpha plus beta, alpha plus I beta x plus e alpha minus I beta x. Okay, that's good. Okay. And y2 is e minus alpha minus I beta x. But y1 e alpha x e I bx plus e negative I bx is 2 e alpha x cosine beta x. So we are going to conclude the cosine here. This one. Okay. So this is 2 cosine beta x. And then the other one, y2 e alpha x this will be 2 to I e alpha x sine beta x. And thus from here, giving you the solutions, that is C1 e alpha x cosine beta x plus C2 e alpha x sine beta x, that is equal to e alpha x C1 cosine beta x plus C2 sine beta x. So this will be the general solutions. So instead of writing with some I here, we can write in more general solutions with using the approach from the Euler formula. Okay, well, I haven't been getting you more detail on this formula, but let's say this is the formula that we can connect the real number with the complex. Okay? But let me just give you what we are going to actually do. Okay? What analytical thinking that we might have. Okay? What kind of observation we need. Okay? So basically, mostly for the second order differential equations, what we are going to do is we are going to see the second order one that has at least second derivative in the equations if we can make out the auxiliary equation or characteristic equations, then we are going to have some sort of quadratic formula. And from that formula, we can see that, oh, probably we are going to have what kind of formula. Okay, from these three cases, the real and distinct, real and equal, and also conjugate complex, we can tailor our solutions. Okay. Let me give you just examples. Okay, I think it's going to be practical, not really that complicated. Okay, we have the second order differential equation. Okay, first, let's say we have 2y double prime minus 5y prime minus 3y. Now, when you know that this is, we know that we probably can have our constant coefficient, and we know that this is the second order, we can directly write this in terms of you can use any symbol. Like, for example, I will write with m, similar with your textbook. So we can write 2m squared minus 5m minus 3. Okay. So this is our characteristic equation or auxiliary equations. Okay. So this is auxiliary equations. And then we know that we can have our factors from here, our roots from our quadratic. Oh, by the way, if we still have trouble finding the roots, okay, let me give you quick tips to find roots easily. Usually you have the let's say x squared plus blah blah blah. You have just one constant right in front of the x squared. You have this, you can make a table and you can check with numbers that are, when you multiply, you're going to have 2m squared. So probably just 2m and m, right? 2m, m. That's the first factors. Okay, and the right one from here. Write all possible numbers. When you multiply, it's -3. So 3, -1. You try first. Oh, I think we can check. It's -2m plus 3m. It's m. It's not -5. So change another one. So we check the other one. For example, we have 1 and maybe -3 because we know it's -5. So -6 plus 1, so it's -5. So this is our root. So 2m plus 1, m minus 3, just on tips, quick tips. So m1 will be -1/2, m2 will be 3. Now the general solutions we have y is c1e -x/2 plus c2e 3x. That's the solution. Okay. For the second one, y double prime -10 y prime plus 25y. So whenever you have this kind of equation, second order, you exactly have y double prime y, just that in your equation. You can directly go to your auxiliary equations, finding roots and finding the general solution. Very fast, very quick. So first here, this will be m squared, okay, minus 10m plus 25. Okay. I think this is very simple. we will just have m -5, right, squared. So we are going to have, in this case, we have m1 equal m2 equal 5. So we have the second case. The second case we have is the general solutions is always c1 e5x plus c2. Instead of e5x, we write x e5x. Okay. It's general solution. Okay, next. Or maybe 3. This 1, 2, 3. We have y double prime plus 4y prime plus 7y equals 0. Now what we have here is we have m squared plus 4m plus 7, and I think this will be having a complex inside, right? Okay, you can go directly either way. You can go for this directly there, or if you want, you can take sometimes to give you more. We can have standard, complete standard form. This will be m plus 2 squared plus 3. So m plus 2 is -3. So m plus 2 is square root of -3 plus minus. And we know that the square root of -1, or it's supposed to be I, right? So m is -2 plus square root of 3i, or m2 is -2 minus square root of 3i. Okay, now we have this. I think it's more faster rather than, but if you prefer the quadratic, yeah, the final answer, then that's the final answer, the general solution. Okay, so if you want to calculate with this, the quadratic formula, it's also okay. You can just plug in all in the ABC. So -4 plus minus 16 minus 4, 7, and then divide by 2. Uh, 28. 16 is 14. So 14. So you need to check that as well. Oh, not 14, 12. Sorry, 12. 12. So this will be 4, 3. So squared 3, 2, right? Yeah, the same. Okay, same. Okay. So we have m1 and m2. Then we know that the alpha will be -2, beta is square root of 3. Then we just plug in to what we have before, e with power of alpha x, so -2x and then C1 cosine squared of 3x plus C2 sine squared of 3x. This is general solution. And notice that we still have the C1, C2, C1, C2, C1, C2. So to find the constant, at least we need two initial value, right? Two initial value. So the other part of the problem is having the initial value, and then you can solve the constant. You can solve the constant. So this is for the second order equation. If you have higher order, actually the pattern will be very similar. Yeah, we'll always show you the pattern, and if you have like third order, fourth order, fifth order, we can solve it also. But of course, this can be happen if we have the homogeneous in a homogeneous equations, homogeneous and linear. But it can be a higher order, not only for first order, but we can solve for second, third, fourth order. But it should be homogeneous, linear. Okay? So one particular skill that you need to have is you need to take a setback for some review of quadratic formula. Quadratic formula. And also polynomial. Polynomial. I think polynomial is more general. Polynomial division, finding roots. Okay, that's I think skills that maybe you will gonna use more in this part. Okay, in this part, solving the auxiliary equation. Okay, before we continue, is there any questions before I gave you the higher order patterns? So this is so in the higher order, we have the theory, the introduction, uh, the superpositions, all of those things, um, the method, the reductions of order. In the homogeneous linear constant coefficient, we can use auxiliary equation. The next one, we still have at least two more sections, undetermined coefficient and variation of parameters. We will skip the Cauchy-Euler equation and the non-linear equations. Okay, we will skip that part. Well, it depends on our progress, I think. Okay. Okay, the next one is still the constant coefficients, but with higher order equations. Okay, let me give you the insight. Okay, to solve the an, okay, ai is for I equal 0, 1, and are real constant. So to solve this, we need to solve the auxiliary, right? We need to solve the auxiliary of the polynomial. Okay? So this will be an become m, okay, m n plus a n minus 1 m n minus 1 plus a2 m squared plus a1 m plus a0. So practically this is the polynomial that we need to solve. Now if all roots are real and distinct, which means the first case, then general solution, we can write y equal c1 e m1x plus c2 e m2x plus dot 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 c and e mx. Okay. But I think for the higher order, it's difficult to summarize the case 2 and 3 because the degree is different. Right? If the degree is just polynomial degree 2, we can see the discriminant from the discriminant. Okay. For example, if we have fifth degree equations, maybe we could have the 5 real roots, or maybe 3 real, 2 complex. Okay. If we have 4, we have 2 real, 2 complex, or 3 real, 1 complex. We have some variations, right? We have some variation for the roots. Okay, and when we have the multiplicity, like when we have the m1 equal m2, we can have some multiplicity. Like for example, if m1 is root multiplicity, let's say how many times, like k times of the polynomial and degree of auxiliary equations, then the solutions, the solutions that is linearly independent from the pattern that we already see, we can have e, let's say we have e m1x or x e m1x. This is also possible, or we could have x squared e m1x, and we could have more and more multiplied with x. Okay? The solutions. and more, okay, until x, let's say k minus 1 m e m1x. Okay. The general solution for the multiplicity, we will have at least we have combinations of e c1 e1 m1x plus c2 e x. Okay, we have some multiplicity if we have. So for this case, for the higher order, we will restrict our case to be having the real solutions, distinct roots, and having a multiplicity. But of course, still we still at the solutions, we might have the the complex root that has its conjugate. Okay, we have the conjugate pairs. Okay, let me just give you an example on what do I mean by this conjugate and complex pair. Okay, let me give you an example. Okay. Okay, again, should be homogeneous, should be linear. Okay, should be linear. So from here, what we have, we can just directly write the auxiliary equation. So m cubed plus 3m squared minus 4. Okay, now it's equal 0. Then we need to solve for m. I think since it's quite simple, we can try some sort of m that we can think. Well, from 0, 1, negative 1. Okay, we can check. If we check m equal 1, suppose that this is equal 0, right? If we plug in 1. So 1 plus 3 minus 4 is 0. So 1 is our root. Okay, 1 root. So my suggestion, okay, to solve the polynomial like this, we could use the polynomial divisions. Or when we know that the one of the root is 1, for example, m1 equal 1 is root, then we can factor out, or we can use the divisions formula from the polynomial. So from here we could write 1, 3, 0, negative 4. So this is for m cubed, m squared, m, and a constant. Okay? And then divide with 1. First we could check, okay? We could check through this. This is plus. This is 0. So it's true that this is under 1 root. Okay. If you don't remember how to use it, basically you need to plus all. So first you need to plus from here. Let me just erase first, okay, to make it clear. So this is the first one is just going through just one, and then multiply this, multiply with one here. The result right here, to plus it, it's 4. The same thing, you need to multiply to here, plus in here, and then the same thing until 0. Okay? So when you have 0, then you completely divide the polynomial. Okay? Now you have the structure becomes m minus 1. This is m squared plus 4m. Okay? Plus 4. This is the factors. And then we could see that clearly from the quadratic here, we can factor m plus 2 squared, right? So we have 3 m's, m equal 1 and m equal negative 2. So m2 is equal, m3 is equal negative 2, m1 is equal 1. So we already have all m's. Now the general solution, y, c1e x, okay, plus c2e negative 2x. But for the third one, write the multiplicity, so we have x in the front, and then e negative 2x. Okay, that's the general solutions. So this is general solutions. So for the higher order, you will have some sort of polynomial analysis. Okay, like when you learn in mathematics, especially for basic mathematics, you learn how to find the polynomial roots. Okay, finding roots for the higher degree of polynomials using the syntactic divisions, trying some sort of roots, whether it's going to be completely divided and make it a 0 or not. Okay. And how many real roots and how many complex roots, you can also try that as well. But I think I don't want to explain that much. Okay, you can review by your own. So from the higher order, you need to find how many roots real, how many roots that are in a conjugate complex pairs, and then you need to write and tailor the whole general solution.
Sorry, Professor.
Yes, yes.
I want to ask, what is the name of this method?
The name is constant coefficient. Constant coefficient.
Thank you, Prof.
Okay. Constant coefficient. So this is the name is the constant coefficient in homogeneous and linear. So the notable restrictions for this method is it needs to be homogeneous and it needs to be linear. Okay. So from all the examples that I gave you, it has the 0 at the right side, right? It's homogeneous. Right? Homogeneous and it's going to be linear. No polynomials here, right? But we are treating the differentials as similar to polynomials, right? Okay. And the results or the solutions is it should conclude or it should include the exponent, the e. Okay. Okay, let me give you an example. So this is the third order. Let me give you the fourth order to give you more idea in the practice. Okay, remember that this is higher order, but still linear. Okay, it's still linear. We can simply write this in terms of y fourth derivative to y double prime plus 1. And since we know this is homogeneous, this is linear, we could try the constant coefficient. We could try that. So we could say that this is becomes m with power of 4 plus 2 m squared plus 1. And since the fourth order, or the polynomial degree 4, is a twice of polynomial degree 2 usually, so we can try to probably factor out and make it as a quadratic one. It's similar to the quadratic one, right? So we could have, let's say, m squared plus 1. If you square this will be getting our equations, right? So this will be the factors, right? So we could equaling this to 0. And then what we are going to do is this will be having this. So we will have some multiplicity, right? We can have multiplicity. So let's say we have multiplicity for m1 and m3. Let's say this is becoming -1, right? So m is plus minus squared of I. So the first one is positive, for example. The second one that has multiplicity is the -1. Okay. Now next, what's happened here? Now we can just write up the general solutions. That's y. First, let's just write the rough solutions. C1 e ix plus C2 e negative ix plus C3 e ix plus C4 e negative should be having the multiplicity, sorry, should be having x e ix plus C4 x e negative ix. Now we can write the grouping. Okay, so we can write the C1 e x plus C2 e negative ex. We can write this as C1 cosine x plus C2 sine x from the Euler formula. And the C1 is different constant. We relabeled another with a new constant. And the x C3 eix, or let me just write with bracket, plus C4 negative ix. We can rewrite this and make it into the Euler C3 cos x plus C4 cos or sine. So the general equations we could write as C1 cos x plus C2 sin x plus C3x cos x plus C4 x sin x. Basically, you just need to rewrite in terms of the using the Euler formula. Because this is when we have alpha is 0, right? And beta is 1. And another way to check, if you remember I think still in the basic of math for polynomials, we might have the rational roots. There is a way to check the solution. Let me give you some tips to check. And basically the tips is just resolving in the polynomial one. Okay, let me give you one more example and tips, and we can have some discussion. Solve the 3y triple prime plus 5y double prime plus 10y prime minus 4y equals 0. Now this is equal to, with the auxiliary equation or the characteristic equation, 3m cubed plus 5m squared plus 10m minus 4 equals. The problem here is we are not really sure on how to solve the polynomials since it's a cube, right? But there is one way to check, okay? It's called the rational root. So first, let's just imagine this will be p, okay? This will be the coefficient. It will be q, okay? The possible roots, okay, let me give you just the method. The possible roots is factor of p divided by factor of q. That is your possible roots. What factor means? If you see this 3 and 4, so let me say 3. Okay. 3 is built by how many numbers if we multiply? It's just 1 and 3, right? Plus minus. There's no other number that is factored from 3. For 4, how many numbers we have? It's plus minus 1, plus minus 4, of course, and plus minus 2, right? So 2 by 2 is 4, 1 by 4 is 4, right? And there is no other number that make it becoming 4, right? And then we could write that as our possible roots. This is roots. Okay. Now the possible roots, factor of p over q, so plus minus 4, right? Plus minus 2, okay, plus minus 1, divided by the factor of q, and then plus minus uh, 4 over 3, 4 over 3, 2 over 3, and plus minus 1 over 3. Okay, so we have 6 possible values, and it has positive, negative, so it's 12 possible values, right? And the way you are going to check is basically trial and error. Check one by one, whether it's the roots or not. But we can use the synthetic divisions like we did before, the polynomial synthetic divisions. That's also one way to check. And also, we could check the Descartes rule, how many variable signs that change in signs. Okay. So it's positive, okay, positive, 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 but it's negative, so one sign change. But I think this is for later part. No need for now. Okay, just checking. I think for checking the synthetic division. So we could write 3, 5, 10, and negative 4. We could check from the easiest one, 1 to maybe just 1 and 2. If we check 1, you see that it's going to be increasing and increasing, and when you get the final result here, it's not equal 0. So that's not our root. And by doing this, we kind of see that when we have some numbers here that is positive, it doesn't really the number is not really going to be equaling the last part, right? So probably take the negative one. This is this is my tips. Okay, probably take negative one. It seems going to be lower, but it's still having not really equal. So when this happens, try the fraction. Okay, so try the fraction. So you don't really need to calculate like from the positive, the bigger number, you check one by one all the numbers. You can just make it small, small, and smaller. So check the 1 over 3. It's 3, it's 1. Okay, it's 5 by 1 is 4, 4 over 3. And then this will be 26 over 3, right? Is it correct? 5, 4. Minus 1. Oh, wait. Should be plus, right? Should be plus, sorry. Should be plus. Oh, okay, we got it. Okay, so one factor that is possible is 1 over 3. So we may write m and then we have another quadratic here that is equal 0. So we have one root that is real, and we have, I don't know what kind of root we have here. So we need to check. So 3m squared plus 6m plus 12 equals 0. So we could write okay, it's another m plus 2 squared equals 0. Is it correct, my solutions? Right, correct, right? So the remaining root is, so this will be m1, m2 is -2, right? Hmm. So this will give solutions. Okay. Okay. Oh, wait. This is wrong. This too, it should be 4 if we want to make that happen. Okay. Yeah. Correct. So this is supposed to be m squared plus 2m. Should be plus 1. So this should be plus 3. Okay. So equal 0. This is m plus 1 squared plus 3. Okay. Now this is correct. Okay. Now we have m plus 1 squared is -3. Okay. And m plus 1 then will be square root of 3i plus minus. So m2 is, let's say it's -1 plus square root of 3i. m3 is -1 minus square root of 3i. Well, m2 and m3, you can say it doesn't matter if you write not in the order. It's, I think it's still okay, because at the very end, your final results will be C1e x over 3 plus e with negative x, because alpha is -1 and beta is square root of 3. Then you can write C2 is cos square root of 3x plus C3 sine square root of 3x. The x is not inside the square root, okay? It's a little bit outside here. Okay. And thus this is the general solution. Okay, so you can write up in your notes that how to write the exchange for the conjugate, especially for the complex root. When you have this, remember that alpha -1 and beta is square root of 3 that you need to write off in your general solution, and it always have this cos and sine formulation in the formula, in the final formula, in the general solution formula. Okay, any questions? Okay, any questions? Okay, any parts that's still confusing? Maybe we need more practice. But I think for practice, I will give practice maybe at the afternoon class. Okay, any questions? Yes. Yeah, time. You want to ask something? Yeah, three case. Yeah, three case. The first one is when you have two distinct roots. You have the multiplicity roots, and you have the complex roots. Okay, any other questions? Okay, let me check. Okay, okay, I think we can move to the, can call this how to solve non-homogeneous differential equations if we have at least second order or higher. We call this, the method is undetermined coefficients. Okay. Let me just give you summary what is the undetermined coefficients. Okay. Okay. Let me write with just my notes. Okay. Because your textbook, I think, too many words. Okay. So we call this undetermined coefficient. Solving non-homogeneous differential equation. Okay, so far we have solved the linear constant coefficient homogeneous equation, right? But how about the non-homogeneous one? Okay. So for linear homogeneous, we can use the constant coefficients, the one that we have before. But if we have the non-homogeneous one, I think I will just give you illustrations on what we have. So let's say we have the y double prime minus 2y prime minus 3y. Let's say it's equal to 3e with power of 2t. We know that this is non-homogeneous, right? Non-homogeneous. First, okay, let's say we have yp, that is our particular solution. If you remember yp from what we have in previous sections. Let's say this yp, let's say the solution, that it can solve non-homogeneous. And we can have, let's say yc, okay, for solving the homogeneous one. So we have the homogeneous is y double prime equals 0. Let's say it's equal to 0. Now, if we check the solutions, okay, if solutions is including yp plus yc, okay, as I think we also have seen this in previous one, but let me just write this to make sure that we understand our concept. So which means that if we try the solutions, so we take second derivative of these two, take first derivative of these two, and just substitute the last one. Let me just write like this. Okay. And this will be equal to yp double prime. And let me just write, this is yp double prime plus yc double prime, or this is y prime, and this will be yp prime plus yc prime. So let me just conclude and write that this is becoming yp double prime minus 2 yp prime minus 3 yp. So I will make this as one all yp, and then plus yc double prime minus 2 yc prime minus 3 yc. Now we know that this is non-homogeneous one, that is 0, and this one is becoming the non-homogeneous, that is 3e to t. So this is equal 3e to t. So this is homogeneous. So we know that from here that y equal yc plus yp also solves non-homogeneous. That we already see also from our previous one. So what is our step, right, that we need to check using this method? So let me just give you the steps. The steps are, let me write back the equations. The first steps, step 1, solve homogeneous. So we write down the homogeneous one, and we can just take this in our auxiliary equations. We can take this m squared. Some books using m, some books using r, no problem. We can take the factor, right? So we have m1 is 3 and m2 is -1. So for the homogeneous, we could write C1 E3t plus C2 E -t. Okay. Now step 2. Find solution for non-homogeneous, or YP. You can call YP. Okay, let me write the non-homogeneous the questions. The questions is having 3e 2t. So the idea, okay, behind this finding this YP is looking at the order of this e. We have 2t, right? So probably this YP also having the same component. Let's say our YP, okay, let YP, let's say equal to AE 2t. And then we could check, okay, we could check this YP as our solution. So we could take the derivatives. So YP first derivative is 2AE2t, and take the second derivative, it's become 4AE2t. Okay. And now we could take this 4AE2t minus 2 by 2 is 4AE2t minus 3AE2t equal 3E2t. Okay. And if this is our particular solutions, then we could take the guess that A, from our guess that A is -1, and it's when we substitute to equation, it's getting the same result, right? So YP is -E2t. Now the step 3 is combining the the general solutions is YC plus YP. So the general solutions, general solution is C1E3t plus C2E negative t minus E2t. Okay. So the way we are letting A, this is we call the undetermined coefficient. So we don't know the coefficient, but we are going to find it. So we can just use any coefficient we want. So it's undetermined coefficient. So that's why we call this undetermined coefficient. Okay. And of course, when we have this C1 and C2 as our constant, we can solve this by initial value problem. So if we have another information of some value for our differential equation, then we can solve C1 and C2 and we can write the final formula. Okay. But there is some limitations and restrictions on how we are going to write this undetermined coefficients. Okay, it seems that we are guessing some numbers, but we need to guess correctly. We need to guess correctly. And sometimes when we have the non-homogeneous one, the right one is in a polynomial, then we need to have some sort of solving through some linear equations. Okay, let me go through one by one. Okay, what we have. So this is from the very simple one, and then a little bit complicated one. But the idea is still the same. The idea in undetermined coefficient is we are just taking A, B, C as our coefficients for our YP, and then combine with the homogeneous one, and that is their general solution. So general solutions for non-homogeneous will always include homogeneous and non-homogeneous. Okay, so non-homogeneous will include we call the complementary for the homogeneous one, and the particular solutions for non-homogeneous, and the whole thing becomes our general solution. Okay. Okay, some restrictions first before we move on to more complicated one. So some restrictions. So some restrictions or some notes. Okay, if we have the y double prime minus 2y prime minus 3y, let me write this 3e negative t. Okay. It's the same formula from the for the left side. So the homogeneous will be the same. Okay, the homogeneous. So first, homogeneous solution is y equal C1e 3t plus C2e negative t. Okay, now when we are using the undetermined coefficient, let me write here. Undetermined coefficient if we let the yp equal a e negative t, then this is a problem. Okay, this is a problem because we have the same structure, the same power e with power negative t. So the problem here is that a e negative t cannot be yp. Then we need to check another guessing, that still it's not scalarly in a ratio. So it need to be, of course, linearly independent. So we need to check another list or another YP that linearly independent, but still has some relation, but it's linearly independent. So we could check YP, for example. Maybe we could take ATE negative T. So we could check this one. So it has T here, so it's okay. It's okay. So we can check if we differentiate this. we could take the product rule, right? Product rule. And then again, and this will be again, let me write, okay. Then we can check our, we can check through our differential equations. So check E negative 2a E negative t, right? Plus a t E negative t minus 2. Okay, I think we can take this cancelled, right? So we have negative 4 ae negative t, 3e negative t. So a will be negative 3 over 4. So y, the solutions, the general solutions will be c1e 3t plus c2e negative t minus 3 over 4 t e negative t. Okay, I think I can give you some table of guessing. So non-homogeneous or non-homogeneity, the right side one, your gas. So if you have, for example, E, then you can guess AE RT. Okay? If you have sine or cosine, you can have A sine RT plus B cosine RT. We need to include sine and cosine as our guess because when we derive sine, it can go for cos. When we derive more, it goes sine, cos, right? So need to have both sine and cosine. And you have degree or polynomial. Then your guess should be a0 plus a1t plus dot 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 plus some an t with power of n. Okay. Depends on how many coefficients you have. Then the steps are going to be the same. We are going to equaling. So first, solving the homogeneous one. Solve the homogeneous one. Second, guessing the non-homogeneous one with some guess. Check that out, and we need to equaling both sides with the guess. Okay, with the guess. And then we can get our constant, and that will be your particular solution. And we need to combine the homogeneous one with this particular solution, and that will be the general solution. I think it's maybe will be better if we are just taking some examples on how we can do this. Okay. I will give you 1 or 2 examples, and then I think we can just stop the lessons for the morning session, and we can continue the afternoon one. I think with more examples to come. So, and also the afternoon session, I will explain on how you are going to have some sort of quiz. Okay, maybe tonight or tomorrow morning. You can. I will give you the link later. The Moodle is still not. It seems still not available, but the course already added to Moodle, but not yet added all the participants and the instructors. So the quiz will be about the first introductions of differential equations, the first order linear. Okay, so just that, the quiz. Okay, any questions first up until here? Any questions? Maybe giving you first example, okay, and then maybe we can discuss more. Okay. Let's say we have differential equation to solve. Y double prime plus 4y prime minus 2y equal to x squared minus 3x plus 6. Okay. Okay, first solve homogeneous, right? This is always to be keep in mind. Solve homogeneous first. Okay. So first we write the homogeneous one equaling 0. So we are going to write m squared plus 4m minus 2. So I think this can be done by plus 4. So this minus 2, this would be minus 4. Okay. So this should be m plus 2 squared, I believe. It's going to be negative 6. So m plus 2 squared is 6. So m plus 2, okay, it's still in real and not complex. So plus minus. So m is minus 2 plus square root of 6. m2 is negative 2 minus square root of 6. So we got the homogeneous solutions. C1e with power of this solutions. We get negative 2 plus square root of x. Okay, and plus C2e negative 2 negative square root of x. Okay, that's our homogeneous. So let me mark this, our homogeneous one. Okay, so we are going to have the particular solution that we see that this having a polynomial, right? Polynomial degree 2. So as our suggestions that gives us that we might have this guess, right? Okay, so we might guess So guessing that our yp is, let's say, ax squared plus bx plus c, okay, to match up with our polynomial degree 2, okay, to match up with this. So what can we do now? We take the derivatives twice and then put into our equations and then equaling both sides, two sides, okay. So first is, let me just write yp double prime plus 4yp prime minus 2yp, and we need to equaling these two sides, okay. So ax squared plus bx plus c, maybe let me write in here. Let's derive first 2ax plus b, and then the second derivative will be 2a, okay. Now we can write 2a plus 4 2ax plus b minus 2 ax squared plus bx plus c. And this is supposed to be equal to this 2x squared minus 3x plus 6. Sorry. 2x squared minus 3x plus 6. Okay, now we are going to group all the variable x. Okay, we are grouped the variable x. So 2a plus 8ax plus 4b minus 2ax squared minus 2bx minus 2c. It's still not grouping, so we group negative 2ax squared plus 8a minus 2b, right? What else? 2a plus 2a plus 4b minus 2c. Okay, I think we already group all. Okay, now the idea is just grouping x squared with x squared, x with x, and the constant, all the constants here with here. Okay, now we can use linear solutions to solve this. We can use substitutions, eliminations. Okay, I think first one is we are going to look this 2a. So negative 2a is equal to a is negative 1, right? And 8a minus 2b is negative 3. So negative 8. So 2b is negative 5, right? So b is negative 5 over 2. And 2a plus 4b minus 2c is 6. So negative 2. 5 over 2, 12 over 2 is 10, so negative 10. 2c is 6. Okay, so this is negative 12, negative 12. So negative 2c is 18, right? So c is negative 9. So we get all these three. So our yp from our equations here is negative x squared, negative 5 over 2x, negative 9. And then we combine these two. Okay, we combine these two. Let me write here that the general solutions is y, c1e, okay, minus x squared minus 5 over 2x minus 9. Okay, that's the general solution. Okay. Okay, any questions? Any questions? Any questions? I think I will just stop until here. We'll give you more examples on what to come in the next afternoon class. Okay. What's your questions, Sam? Yes, finding homogeneous, and then the second one is guessing the particular solution. And then after we guess, we check, and then equaling with the right side, with the non-homogeneous, the right side one. Okay. So basically, this undetermined coefficient is you're going to trial and error some guessing that you have made, and then check, and then equaling both sides, and that will be your particular solution. Okay. I think we will go more into some example, because there are more and more examples in this undetermined coefficient, because we have some sort of forms that we are going to have. Like I gave you the table here, right? We might have the exponent, sine or cosine, and we might have the degree of polynomial, and we might have combination of both. And I will tell you how to combine both solutions. Okay. Okay, I think topic about the test. Oh yeah. Forgot to see. Can you repeat the topic for the the topic for the test? Let me just write in the notes. Okay. So the quiz will be the intro. This is actually introduction of differential equations. Like we know the first order, right? We know second order, how to differentiate it, what is linear and nonlinear, something like this. Okay? How to classify that the intro. The second one, we have the first order. The first order differential equations. We have several methods, right? From the separable, the linear, the exact equations, substitutions, right? And also, before this, we also have the slope field, right? The solution curve, the slope field, autonomous order, right? Autonomous order to see the behavior of the graph, right? All right, just this one, just these two. Okay. And you need just to ask to click the link, and then prepare maybe paper, calculators, books. It's open notes, so all the exam we have will be open notes. So don't worry about, you don't really you don't really need to memorize. What you need to at least memorize is the logic and steps. Okay. The details of the formula you don't need to remember. Okay, I think that's all for today. For this morning, we will see you again in the afternoon. Okay. Okay. If you have questions, you can ask in the afternoon class. Okay. So thank you all. So we'll stop the recording.